Okay, hi. So in this video we're going to go through the entire Physics Unit 2 paper from May or June 2014. Now this is the AQA higher paper, so if you're doing foundations, some of this won't apply to you, but we're going to go through the entire paper question by question. So as usual, if I'm going too fast, please feel free to pause the video and go at your own pace. But let's take a look right now at the first question. So, here it says figure 1 shows a slide in a child's playground, or a children's playground. A child of mass 18 kilograms goes down the slide. The vertical distance from the top to the bottom of the slide is 2.5 meters. So I'm going to quickly label that straight away, because that's clearly important. Alright, so we've got 2.5 meters vertical distance there. It asks us to calculate the decrease in gravitational potential energy of the child sliding from the top to the bottom of the slide. Now, it tells us that the gravitational field strength is taken to be 10. Sometimes it's 9.8, but we are told in this case it's 10, so that's fine. And we're going to use the correct equation from the physics equation sheet. As usual, I would rather you remember these than just rely on the sheet, but if we have a look at the sheet, we can make sure that we are correct. Now, you should know that the equation for gravitational potential energy, I'm just going to put E there, but that is obviously GPE, gravitational potential energy, is equal to mass times by gravitational field strength times by h, where h there is the height or the change in height, okay, because we can never describe the actual gravitational potential energy, we describe the change in gravitational potential energy. So it's m times g times h, and we just fill those in because you have to make sure the units are correct. 18 kilograms, right, because we're told that the child has a mass of 18 kilograms, times by, well, g we're given as 10, right, and that is newtons per kilogram, times by our height in meters, which is 2.5 meters. So I'm just going to put 2.5 in there. Calculate that and you get a grand total of 450. Okay, and that is in joules because we're talking about energy. And so 450 is our answer. All right, let's move on. Now, in question B, it says the slide is made of plastic. The child becomes electrically charged when he goes down the slide. Explain why. Now remember, this is talking about static, alright, so static electricity. Right, I'm going to put that in brackets so you know what we are talking about. The child becomes electrically charged. Well, I mean, obviously the child is wearing clothes. Okay, that's a given. We are shown in the question, you can see the child there, he's wearing jeans and a shirt or whatever. Right, and static electricity comes as a result of friction, okay, between two things. Now, you are given the example that cloth and plastic, a plastic rod, right, when you rub those two together you get friction, which leads to transfer of electrons. Now this is the same thing, except rather than a rod we've got a slide, and rather than just a cloth we've got the child's clothes, and so we have friction between clothes and the slide, okay, cause electrons to be transferred between the clothes and the slide. Okay, that's enough. I'm just going to say that equals charge, because when you have electrons transferred, you then will have something which is positive and something which is negative charged. Alright, so let's move on. Oh, sorry, let's go back up slightly, there we go. So in B part 2, going down the slide causes the child's hair to stand on end. What conclusion about the electrical charge on the child's hair can be made from this observation? Now it's easy in this case to think, well, I don't know whether the child's hair is going to be positive or negative, and in fact it doesn't matter, right? The first thing to say is that all charges on the hair are equal or same, right? We're talking about like charges. So you're going to have negatively charged hair or positively charged hair, but all the hair will be the same charge, right? And the reason we know that is because if the child's hair is standing on end, the individual hairs, are repelling each other. So hair repels other hair as like charges repel If the hair could be positive and negative, then parts of the hair would attract each other, right? And that's not what we see, and that's why it stands on end. Now, B part 3 says, why would the child not become electrically charged if the slide was made of metal? Now, for static electricity, we need two things to rub together, which are insulators, okay? But metal is a conductor. So metal is a conductor, not an insulator. Okay, static means staying where it is, right? So on an insulator, the charge can stay where it is, whereas on a conductor, the charge will move through the metal, right? So I'm going to put in brackets here, charge would pass through the metal and to the earth, right? Because that's what the charge would do, because the metal slide would be in contact with the supports, which are also metal, and so charge can literally get from the slide to the earth, right? And that stops it from remaining charged. Okay, right, so let's move on. That was question 1. So question 2, it says that stars go through a life cycle, right? We should all know that. Some stars will finish their life cycle as a black dwarf and other stars as a black hole. Table 1 gives the mass relative to the Sun of 3 stars, J, K, and L. Which one of these stars, J, K, or L, will become a black dwarf? Alright, now you should know that only stars which are similar masses to the Sun, right, so similar masses or maybe even smaller, will go on to become a black dwarf. Larger stars will obviously go on, well, they're going to go on to become supergiants and so on. So in this question, when it says which one of these will become a black dwarf, well, that is going to be J, because it's the only one which is close to the mass of the Sun. Because K and L, well, K is 14.5 times bigger than the Sun, and L is 20 times bigger. So that's way too big. So that's exactly what we're going to say in our reason. Only J is similar size to our Sun. This is required to become black dwarf. Alright, let's carry on. So 2b. Scientists can take measurements needed to calculate the mass of many stars. Scientists cannot calculate the mass of the star. Now, I'm going to struggle to pronounce this. Betelgeuse. That's probably completely wrong. They estimate that the star has a mass between 8 and 20 times the mass of the Sun. Right, now this star, not going to pronounce it again, is in the red supergiant stage of its life cycle. Right, this is important, the red supergiant stage. What will happen to the star at the end of the red supergiant stage? Well, in this stage, you should know that when it reaches the end of this, it's going to end in a massive explosion, right? And we have a particular word for that explosion, and it's known as a supernova, okay? So the star will explode. Okay, and that is what we call the supernova. All right, now that is only worth 1 mark, so we don't have to go into any more detail than that. All right, let's have a look. At B part 2, it says suggest one reason why scientists can only estimate and not calculate the mass of this star. Now, clearly this star is extremely far away, right? So we can't actually put it on a set of scales, right? You can't do that with any star, of course. It sounds ludicrous. So what we're actually doing is we're using certain readings to make estimates. We can't physically measure the mass directly. So simply, we cannot take the physical measurements required. Okay, right, you could have got the mark in this question for a few different answers. You could have quite simply said that we don't at the moment have the technology, because in the future, who knows, maybe we're going to be able to measure the mass of any star. All right, that leads quite nicely on to the next question, because it says in future it may become possible to calculate the mass of that star. Suggest reasons why. And you can say, well, advances in technology may allow this to be calculated. Alright, it's only a 1 mark, and you don't have to go into any more detail than that. You don't have to, make a theory as to how we're going to do it. That's certainly way above GCSE or anything I've ever done. Alright, so in 2C it says describe what happens to a star after the main sequence period, right, this is really important, after the main sequence period, for the star to eventually become a black dwarf. Right, so what we're talking about here is the star which is close to the size of our sun. The much larger stars will go down a different pathway because they're not going to form a black dwarf at all. What they're going to form is, of course, a neutron star or a black hole following a supernova. Alright, so what I'm going to say is following main sequence star. Now the main sequence is when you have something which looks like our sun. Our sun is currently a main sequence star because it's not expanding or contracting, okay? It's basically even. So forces of expansion and contraction are the same, so you've got a star which is stable at the moment, right? That's what a main sequence star means. Now those two forces are obviously as a result of pressure from expanding gases. The gas is obviously really hot, it's expanding and going outwards, but that's balanced by the force of gravity pulling inwards. Alright, so what's going to happen then? Well, first of all, the star expands. So you have star expands and forms a red giant. Okay, important, it's a red giant, it's not a red supergiant. Alright, so what then happens is that nuclear fusion is occurring. That's always occurring in the star, but in general, in a stable star, it's going to be hydrogen fusing to make helium. But once you're using up all your hydrogens, then helium starts to fuse to make the heavier elements. So nuclear fusion occurs and forms heavy elements. I'm going to put in brackets here, lighter than iron, because you should know that iron and the elements which are heavier than iron are formed in supernovas, and that is a different pathway. Okay, they are not formed in this pathway because there's not enough energy. Supernovas allow the formation of the heavy elements which are heavier than iron. Alright, so this nuclear fusion is important. This will then cause the star to shrink. So star, well, let's say the star shrinks, alright, becoming a white dwarf. Right, the reason why it's shrunk is because the gases aren't expanding as much as they were before. Fusion is using up all the hydrogen, okay? Helium is then being used and we're forming other elements, and this is not sustainable. It can't go on for too long, and so you get this white dwarf formed, okay? Right, as fusion gets slower and slower, the star is then going to cool down. So the star cools down and will eventually fade. Alright, because obviously the fact that we can see the stars is a result of radiation being emitted, some of which is light, right? We can see stars because light is being emitted, but loads of other types of radiation are also being emitted. Now, eventually, star stops emitting, or releasing if you like, but emitting is the better word, radiation, which equals a black dwarf. Alright, because when it stops emitting radiation, we can't see it because no light's being given out, and so therefore it is a black dwarf. And that is good enough for 5 marks, right? We've gone into a bit more detail there than you really need to. What you really need to say is that the star expands originally to become a red giant, alright? Then nuclear fusion occurs, which causes the star to then shrink and form a white dwarf. And when it cools down and radiation isn't emitted anymore, you get a black dwarf. Alright, and that is question 2C. Alright, so moving on, we now have question 3. So 3A says that figure 2 shows horizontal forces acting on a moving bicycle and cyclist, right? We haven't shown the vertical forces here because obviously there's going to be a reaction from the floor and the weight of the cyclist and the bike. So 3A, it says, what causes force A? Now force A is this force here from the back wheel. And it says draw a ring around the correct answer. Now that is obviously going to be friction. You know that straight away because gravity and weight work vertically. Okay, friction is the one that works horizontally. Friction is the driving force. Okay, so between the wheel or the tire and the road, right? Friction is going to cause the bike to actually move forward, because if there's no friction, imagine driving on ice, then the wheel just spins and you don't move forward. All right. It then says what causes force B. Now B, if we take a look, is going backwards from the cyclist. Right, now the cyclist is obviously not cycling in a vacuum, and so what's causing force B is air resistance. Okay, right, you could have said wind resistance, you could have said drag, but air resistance is probably the best one. All right, question 3A part 3. It says we're going to be assessed using good English. All right, so figure 3 shows how the velocity of the cyclist changes during the first part of a journey along a straight, level road. During this part of the journey, the force applied to the cyclist, by the cyclist to the bicycle pedals is constant, right? And we have a curve here. So that basically tells us that because we're on a straight, level road, right, we can't say, oh, the cyclist is going down a hill and then he's going uphill or whatever, right? It's flat, it's level, and so we need to come up with something else. Question 7. Sorry, not question 7. This is page 7. It says, describe how and explain, in terms of forces A and B, why the velocity of the cyclist changes. Right, between points X and Y, and between points Y and Z, all of which are marked on the graph. Let's have a look up here, and there we can see them. So X and Y, we've clearly got the velocity increasing, right? And Y and Z, the velocity is moving towards becoming constant. So let's have a go at explaining this, right? It's a 6-mark question. Now, this is very similar to a common example, which is someone jumping out of an aeroplane, so a skydiver, right? However, this is on a bike and it's along a flat road. The important thing here is that we are told that the force going forwards, right, so the pedaling force is constant. So if I quickly go back up and have a look at the graph, we can see that at X, obviously we are accelerating, right, because the velocity is going up and up and up and up, so acceleration is occurring. Now here, the graph starts to dip, right? We are still accelerating because the velocity is still going up, but we are not accelerating as much as we were here because the graph is not as steep. All right, so what I'm going to say to start off with is that initially there is no force B. Right, now force B is your wind resistance. At X, so point X, force B is smaller than force A. Driving force equals a positive resultant force, and therefore the bike accelerates. Okay, sorry, that was a bit of a mouthful. What I'm saying here is that because the driving force is greater than the force of resistance, we have a positive acceleration, right? So the velocity is increasing. Okay, importantly, as velocity increases, wind resistance increases, or air resistance increases. Air resistance increases also. Okay, because air resistance is actually proportional to the velocity. Okay, so as we approach point Y, velocity is high, and so force B is closer to force A. Right? Acceleration still occurs, but it is not as great. Sorry, let's rub that out. Not as great as at point X. Okay, so what I'm saying here is that as the air resistance goes up, the resultant force obviously isn't as large, and so the acceleration isn't as large. But we are still accelerating because it's not a horizontal line at point Y, right, as you approach point Y. So let's have a look at the graph quickly, and you'll see what I mean. At point Y, we still, if I was to draw a tangent, right, that is not horizontal. You still have acceleration, okay? But it is not as large as it is down here, because if I draw a tangent at X, this isn't a straight line, obviously, but you get the idea. Obviously, that's way steeper than this, and so our acceleration is way higher. So that's good enough between X and Y, and now we talk about between Y and Z. So at Y, the velocity is still slightly going up because we still have acceleration until we hit about this point here. And if I were to draw a tangent at that point there, we get this flat line, right? That means that acceleration is now 0. Acceleration is 0 because the resultant force is 0, okay? So that means that force A and force B are now equal. So let's have a go at writing that. I'm going to write it down here just so I've separated it from the rest. But obviously in your exam, you're not going to leave gaps that big. All right, so at point Y, acceleration is low, but velocity is still increasing. Okay. As we approach point Z, the line is flat, which equals 0 acceleration. Okay? This means that air resistance is equal and opposite to driving force, which is of course friction between the tyres and the road. Driving force and resultant force is 0. Okay, we have reached terminal velocity. Okay, right, so that was a long question, but it is a very good one. It's a very common question that comes up when you have to explain how something reaches terminal velocity if the driving force remains constant. So let's move on to part B. So here in B part 1, we've got the cyclist used the brakes to slow down and stop the cycle. A constant braking force of 140 newtons stopped the bicycle in a distance of 24 meters. Calculate the work done by the braking force to stop the bicycle and give the unit. Alright, so it tells us to use the correct equation from the physics sheet. Obviously, don't like having to revert to those, but if you need to look at it, then do so. Now, work done is equal to force times by the distance in the direction of the force, right? Now, all we need to do is plug our units in. But one thing I want to say is remember that work done is equal to energy transferred, right? So this is why we need to be careful with our units. So work done is equal to force times distance, and that is force in newtons and distance in meters. And luckily, we don't actually have to convert anything because we have those. So that is equal to 140 newtons times by 24 meters, which is going to give us an answer of 3,360 Newton meters, right, if we were timesing newtons by meters. Now, very important, we never quote work done in Newton meters, right? Newton meters is equal to the correct energy unit, which is the joule, right? And that is a capital J, important. If you put a lowercase j, they will actually take a mark away because it does say give the unit. So I'm going to say 3,360 and joules, and that is your answer. Moving on to part 2. And there we go. It says complete the following sentences. When the brakes are used, the bicycle slows down. The kinetic energy of the bicycle, and we need one word, decreases. If something slows down, then kinetic energy is reduced because kinetic energy is proportional to velocity squared. At the same time, the something of the brakes increases. Well, the kinetic energy is converted into other types of energy. A major component of that is thermal energy. It heats the brakes up, and so we're going to say the temperature of the brakes increases, right? I could have said thermal energy because the thermal energy did increase, and they would have perfectly give us the mark for that as well. All right, and that brings us to the end of question 3. So let's now scroll down. All right, so let's have a look at question 4. It says that figure 4 shows the apparatus used to obtain data needed to calculate the resistance of a thermistor at different temperatures. Right, so we've got this circuit here, and down here we've got a thermistor, but you can see that the symbol there is covered up. That's probably going to be a question. And we have a Bunsen burner, a thermometer showing us different temperatures, and we're going to be measuring the resistance. All right, so surprise, surprise, the first part, 4A, asks us to draw the circuit symbol for a thermistor. So this is just something you need to know, and it's basically a resistor, right, which looks something like that. Actually, I'm going to make sure the whole thing fits in the box. So it's a resistor, looks like that, but you have this symbol going through it, which tells you it is a thermistor and is related to temperature. All right, so simple enough. Part 2, we are asked to use the data given in figure 4 to calculate the resistance of the thermistor at 20 degrees Celsius. And it says use the correct equation from the formula sheet. And so let's go back up and have a look what data we are given. Well, we're told the reading on the ammeter is 0.025 amps, and we're told that the reading on the voltmeter, all right, which is in parallel with the thermistor, which is important there, is 9 volts. All right, so basically we want resistance, we have voltage, and we have current. So we're going to be using the equation V is equal to I times R. All right, we just fill in the numbers. 9 volts is equal to our current, which is 0.025 amps, multiplied by our resistance. Therefore, we rearrange and we get resistance is equal to 9 divided by 0.025. Right, because it's times here, we do the opposite, which is divide to get R on its own. And that will give us an answer of 360 ohms. That's the symbol for ohms, but because we're given the units anyway, we just need to fill in 360. All right. Okay, right, next page. In part 3, we are shown, or we're told that figure 5 shows the axis for a sketch graph, right? Complete figure 5 to show how the resistance of the thermistor will change as the temperature of the thermistor increases from 20 to 100 degrees Celsius. All right, now this is a sketch, okay? This is worth 1 mark. We don't have any values on the Y and the X axis. So we just need to draw the shape of the graph. We don't need to put any values in. All right, now a thermistor is special because it is related to temperature and it reacts in a different way than everything else does when the temperature is increased, right? When temperature increases, in general, resistance increases. However, a thermistor is special because whenever temperature is increased, the resistance decreases. Okay, that's why it's called a thermistor, because it doesn't behave as things normally do when temperature is increased. So, what we're going to have is that, let's say, for example, that this was 0. We're not going to put a point here. I'm going to say that the resistance is going to start off at some high point, and it is going to get lower and lower and lower and lower as the temperature increases, right? But as the temperature carries on increasing, okay, the resistance is going to approach 0. Okay, that's why it's not a straight line. It's going to approach 0, but it's never going to go below 0. You're not going to have a negative resistance, all right? So the relationship is like this. You have a curve rather than a straight line relationship between resistance and temperature. Alright, so let's have a look at part 4. It says, which one of the following is most likely to include a thermistor? And we're asked to tick one box. And we're told an automatic circuit to switch a plant watering system on and off. Automatic circuit to switch an outside light on when it gets dark. An automatic circuit to switch a heating system on and off. Now, obviously, only one of those is actually directly related to temperature, because to switch a plant watering system on and off, then you're going to want to sense the water, right? Not the temperature. The light, okay, that you might think that that's sort of related to temperature, but not always. Sometimes, when it's dark, it could be really cold, or sometimes it could be really warm, so it's not direct. But a heating system, okay, that completely depends on the temperature, right? When it's cold, you want the heating on. When it's hot, you want the heating off. And so that's why we're going to use a thermistor. And that's pretty straightforward. Now, 4b says the ammeter used in the circuit has a very low resistance. Why is it important that ammeters have a very low resistance? Well, this is because ammeters are reading the current, and if an ammeter had a high resistance, then it would alter the current, okay? So you wouldn't actually be getting a true reading of the current without the ammeter. So this is that so that the ammeter itself doesn't affect the current or I'm just going to say slash reduce the current, because a high resistance or an increased resistance leads to a reduction in the current. Okay, so this is so that the ammeter doesn't affect or reduce the current, or affects it as little as possible, because it's going to affect it a very, very tiny amount. And that will be our answer. That's good enough for our mark. Oh, slightly too far there. Let's have a look at 4C. It says the table gives the temperature of boiling water using 3 different temperature scales. Right, so we've got Celsius, Fahrenheit, and Raumur. All right, I think I'm pronouncing that right. Scientists in different countries use the same temperature scale to measure temperature. Suggest one advantage of doing this. Now this means that all readings can be completely understood, because if everyone used different temperature scales, then of course, you know, you might be reading a bit of data and it will be confusing because the temperature looks really strange. That's just because it's in a different scale. So allows universal, that just means of everyone, universal understanding of data. All right, let's move on to 4D. A student plans to investigate how the resistance of a light-dependent resistor, LDR, changes with light intensity. The student starts with the apparatus in figure 4, okay, which we've already seen, but makes 3 changes to the apparatus. One of the changes the student makes is to replace the thermistor with, obviously, the light-dependent resistor. Describe what other changes the student should make. All right, so let's quickly go back and have a look at the apparatus. So here we are here. Let's rub out my drawings there. So what we've already done is we've replaced the thermistor with an LDR, which is good, but we don't need this Bunsen burner, do we? So we're going to swap the Bunsen burner, because we're not measuring temperature anymore. We're going to swap that for something which is going to give out light. For example, a lamp or a light bulb or whatever we want. Okay, so a light source. So we're going to swap Bunsen burner for a light source. And the thermometer, well, how are we going to measure the amount of light? Well, we're going to have something which senses light, which is a light sensor, rather than a thermometer, because we don't care about temperature. So that's 2 things straight away, okay, because it says 3 changes and we need 2. So replace Bunsen with a light source. Okay, that's 1. And then the other one is to replace the thermometer with a light sensor. All right, and then that brings us to the end of question 4. So in question 5, we are given figure 6, which shows a skateboarder jumping forwards off his skateboard. The skateboard is stationary at the moment the skateboarder jumps, right? So you might have tried this when you were younger. If you've got a skateboard sitting on the floor and you jump forward, the skateboard is going to roll backwards. So question 5a says the skateboard moves backwards as the skateboarder jumps forwards. Explain using the idea of momentum why the skateboard moves backwards. Now, the first thing that we need to realize is that we're going to use, I'm going to put this in brackets actually. Okay, we're going to use the idea of the conservation of momentum. And what that states is that the total momentum before and after an event is going to be the same, so it's going to be equal. Now, if everything is stationary before the jump, then that means that the total momentum is 0, right? So that means that the total momentum after the jump also has to be 0, okay? Momentum has direction, and if the skateboarder is jumping forwards, then the skateboard itself must move backwards to give an equal and opposite momentum, giving a total momentum of 0. So what I'm going to say is that the total momentum before is equal to total momentum after the event. Alright, so that is just basically the conservation of momentum. Before the jump, as I say, the momentum is 0. Okay, so I didn't write total there, so I'll put in brackets there, total. The total momentum before the jump is 0. The skateboarder jumps forwards and therefore has a momentum. Alright, the skateboard must move in the opposite direction with equal momentum to obey the law of conservation. Alright, so that basically means that the skateboarder and the skateboard, now that they're moving, obviously they both have a momentum, because momentum is mass times velocity, and they must cancel each other out in order to satisfy the conservation of momentum. And that is perfectly fine for 3 marks. Alright, so let's have a look at 5b. So in 5b, we're told the mass of the skateboard is 1.8 kilos and the mass of the skateboarder is 4.2 kilos. And it says calculate the velocity at which the skateboard moves backwards if the skateboarder jumps forwards at a velocity of 0.3 meters per second. It tells us to use the correct equation from the physics equation sheet. As usual, would rather remember it without the sheet. Now remember that the total momentum before is the same as the total momentum after the event. The total momentum before the event was 0, and so the total momentum after the event must be 0. So what I'm going to say is that 0 is equal to the momentum of the skateboarder, which was, well, let me just write A for the skateboarder and I'll write B for the skateboard, right? So MA VA, right, which is the mass and the velocity of the skateboarder, plus MBVB, mass of the skateboard times velocity of the skateboard. And it's this VB that we are after, which is the velocity. Alright, so 0 is therefore equal to the mass of the skateboarder, which is 42 kilos, times by the velocity of the skateboarder, which was 0.3. Alright, and I'm going to say plus the mass of the skateboard, which was 1.8, times by the velocity, which was VB, and that's what we're trying to find. Okay? So if I put this into my calculator, I'm going to get that 12.6 is the momentum of the skateboarder. All right, 12.6 plus our 1.8 times by VB, our velocity, right, equals 0. And now all I'm going to do is I'm going to take this onto the opposite side. So I'm going to minus 12.6 from both sides, all right, and I get negative 12.6 is equal to 1.8 times by VB. And if I want to opposite a times, I do divide. So I'm going to divide by 1.8, divide by 1.8 to get VB on its own. And that gives me an answer of -7. Okay, and that is the velocity of the skateboard. Right, so my answer is going to be -7 meters per second. All right, now you would have got all the marks if you'd have said 7 meters per second. I much rather say -7 because the skateboard and the skateboarder are traveling in opposite directions and velocity has direction. So the fact that it's negative means it's moving in the opposite direction to the skateboarder. All right, but you would have got all the marks even if you hadn't have put a negative on the end. All right, let's move on now to question 6. Alright, so question 6, it says there are many isotopes of the element molybdenum. Okay, what do the nuclei of different molybdenum isotopes have in common? Now, isotopes, it means the same element, alright, but with a different mass number. And that means that they have the same amount of protons and a different number of neutrons. And obviously electrons, we're not even going to mention them because they're not in the nucleus. So we're going to say same number of neutrons. Oh, sorry, not neutrons. That's what they have. Different. Same number of protons means the same element. Alright, so same number of protons. The isotope molybdenum-99 is produced inside some nuclear power stations from nuclear fission of uranium-235. What happens during the process of fission? Now, you can probably already tell, even if you didn't know, from the numbers. All right, molybdenum is clearly smaller than uranium, and that is because the nuclei are going to split. So, nuclei split into smaller nuclei. All right, that's what happens in fission. Now, B part 2, it says, inside which part of a nuclear power station would molybdenum be produced? Now, again, it is a reaction, okay, which is going to produce that molybdenum, because obviously we're starting off with uranium. So where that's going to happen is in the reactor. So in the reactor. You can say nuclear reactor, that's correct, but the reactor part is what they're really looking for. So, that was pretty easy. 6 part C. When the nucleus of a molybdenum-99 atom decays, it emits radiation and changes into a nucleus of technetium-99. Alright? Now this means that they've actually changed into a different chemical. Right? Molybdenum and technetium are not the same thing, but you can see that they have the same mass number. Right? The atomic number has actually changed. So which type of radiation causes this to occur? Well, that is beta. Right? I'm going to put beta, or in brackets, beta radiation. Okay, and give a reason for the answer. As I just said, the mass number hasn't changed, but the atomic number has. So atomic number increased, mass number stays the same. Now, we know that this is true because in beta emission, a neutron is basically converted into a proton and an electron, right? So the neutron changes, but the neutron changes into a proton, right? But because they have the same mass, it means the mass number stays the same. An electron is emitted, but electrons are so light that they're not included in the mass number, right? And that's how we know. So we could have written that as well. We could have said that beta emission is when a neutron is converted to a proton and an electron, and that would have gotten us some marks as well, or the mark as well. Alright, so 6D, it says technetium has a short half-life and emits gamma radiation. What is meant by the term half-life? Now, there are a few definitions of half-life, and I'm going to use the most obvious one. This is the time taken for the number of radioactive nuclei to halve, right? So if you have a radioactive material, the time taken for you to have half of that radioactive material left is the half-life of that substance, and that half-life is constant, and so it doesn't matter how much of it you've got. All right. 6E, it says technetium-99 is used by doctors as a medical tracer. In hospitals, it is produced inside a technetium generator by the decay of molybdenum-99. Figure 7 shows the number of nuclei in a sample of molybdenum, or how the nuclei changes with time as the nuclei decay. So that was a bit of a tongue twister. It shows how the number of nuclei in a sample changes with time as those nuclei decay. All right, and so let's go down some more. It says a technetium generator will continue to produce sufficient technetium-99 until 80% of the original has decayed or have decayed. After how many days will a source of molybdenum-99 inside a technetium generator need replacing? Show clearly your calculation and how you use the graph. All right, so it says 80%. Okay, and luckily we start at 100,000, which makes this calculation actually pretty simple. Now, when 80% has gone, we have 20% left. And 20% of 100,000 is 20,000, which is down here. All right, and there it is on the graph. So I'm going to say there, because that follows this line. And how long did it take for the number of nuclei to drop from 100,000 to 20,000? Well, what we need to do is we need to read the time in days, and it's 1 square after 6. Okay, so let's just have a look how much each square is worth. Well, there are 5 squares between 6 and 7, so each square is 0.2. So if you go 1 square on top of 6, it makes 6.2 days. All right, and so let's just go back down to the question. There we go. And so we have at 20,000 nuclei from graph, I'm going to put in brackets here, from graph equals 6.2 days. All right, so number of days is 6.2. Next, it says medical traces are injected into a patient's body. This involves some risk to the patient's health. Explain the risk to the patient of using a radioactive substance as a medical tracer. Now, there are lots of different theories for how it is harmful, but there are a few which you should know, and they are definitely true. One of those is that radiation can be ionizing, which is harmful to health. Right, and it wants 2 marks, so why is it harmful to health? The radiation can kill living cells and also cause mutation of DNA. All right, so living cells can be harmed and killed, and mutation of DNA, it happens as a result of ionizing radiation. So now E part 3, it says, even though there may be a risk, doctors frequently use radioactive substances for medical diagnosis and treatments, and it says, suggest why. Now this is only a 1 mark question, and it might seem a little too obvious to you, but it's because the benefits of using the radiation are way better, well, they way outweigh, if you like, the risks. So there are loads more benefits than there are risks, because a small amount of radiation is often harmless. So benefits of treatments / diagnoses outweigh the risks. All right, and then that would be the end of question 6. So question 7, we've got figure 8 shows an electric drill. Right, so we've got this drill here. You've probably seen one of these in real life. We've got these plastic handles, plastic grips, plastic cover, and a 2-core cable. They're clearly all important. The information in the box is taken from the booklet supplied with the drill. It says the drill is fitted with a 2-core cable. The power supply, 230 volts AC, 50 hertz. Right, hertz is frequency, volts is your power supply, your potential difference. Power input, 1012 watts, and the mass of the drill is 6 kilograms. Now it says, why is it safe for the drill to be fitted with a 2-core cable rather than a 3-core cable? So a 3-core cable, you should know, is used when you have a metal cased appliance, because we need to earth just so that the metal casing does not come into contact with the live wire and become live itself. We can see from the plastic grip, the plastic cover and the plastic handle that this appliance has a plastic case. So plastic case, and plastic is an insulator, right? So appliance does not need to be earthed. All right, next, let's have a look at 7b. It says calculate the current drawn from the mains electricity supply to the drill. All right, so if we go back up and have a look at our values, we have a power supply of 230 volts. We have a power of 1012. Now notice we're told nothing about the resistance, right? So we're not going to use that equation. What we are going to use though is power, voltage, and current. And the equation which relates those is power is equal to voltage times by current. P equals VI. Right, so power is 1012 watts, and that is equal to our voltage, which is the main supply of 230 volts, times by our current, which is going to be in amps. Now to get current on its own, we're going to divide both sides by 230, because obviously it's current times 230. So the opposite is divide, and we get 1012 over 230 is equal to 4.4, and that is in amps, and that is equal to our current I. So we're given amps in the answer, so all we need to write down is 4.4, and there we go. Okay, let's move on. So 7c, we're told it's advisable to use all 230 volt power tools with a residual current circuit breaker. How does a RCCB operate? Now you should know that these are basically more sophisticated versions of a fuse. A fuse will blow when the current is too high, but a RCCB, a residual current circuit breaker, basically detects differences in current, right? And those differences in current are between the live wire and the neutral wire, So basically it detects differences, right? And I'm going to put in here slight, so even really small differences, and that's why they're better than fuses, slight differences between the live and neutral wires, and shuts down if different. So if those currents are different, right, and it's very sensitive, so even if they're just a little bit different, it will shut the appliance down and stop it from malfunctioning. Okay, so that is the end of the video. Now, I hope you're able to follow that. We did go fairly quickly, so if you weren't able to, please feel free to rewind, pause the video as you like. But please do like and subscribe, because there are more videos just like this coming very soon. If you have got any questions on anything covered in the video, please feel free to write a comment in the box below, or send me a direct email using the link in the description, and I'll be sure to get back to you. But I look forward to seeing you in the next one.